I spent like the last hour and a half trying to get a webcam to work for this accessibility training course. Should have been doing other stuff.
Oh.
But let's go to RStudio. Alright, so we are live. We are shorthanded. And I would guess that most people will not be watching this virtually. Just have a funny suspicion. Let's see here. Normality practice. Yeah, it is. It's a Friday. That could contribute to it. Oh, we've got one more.
Sorry, I was advising. Unset.
I don't think we need strings and factors. All right, so this is where we're at. So just so we have it, I uploaded 2 homework sets. So the first one is the normal probabilities, so using the tables, using p-norm function, and so forth. I have that due date set on Monday, so you can work on it in lab if you wanted to. I would definitely try to work on it because that's going to appear on the exam. And then I've already posted the Normality Practice homework assignment. So, it's, again, kind of what this is, just reinforcing, making the histograms with the curve, doing QQ plots and interpreting them, running Shapiro Test. All right, and that's posted. I think I set the due date also on Monday at the end of the day. I don't think either of them should take very long. It's just kind of test. Can you do it? And the reason I did that is because we have an exam coming up next week, not this coming Monday, but the following Monday is our next exam. So that should be on the 18th. All right, so we'll do that exam in lab. It is, I would say, it's tentatively scheduled for lab right now. And the reason is because that should be our second candidate, job candidate should be coming in. And I'd like to see the teaching and the research demo. So once Dr. Skipper finalizes the schedule on when stuff is going to be presented, if his research happens to be during our lab time, at let's say 2:45, what we'll probably do is do the closed book portion during our 11 o'clock lecture, and then the lab will be all of the application part that I can get out of here to go see that talk. And if I leave to go see the talk and then come back and you're still working on it, you're still working on it.
You think I'm going with Normality? Yeah.
What's that?
You want to do that?
Yeah, it's so tentatively, but it's going to be that day. So we're kind of we're getting close to hitting all of our material that's going to be on the exam. So this is where we left off. This is Normality Practice. All right, so I did Normality Practice.csv, and this was a slightly different one. So when I started pulling it into R, it didn't register the headers for me. It actually, in the data frame that it would have read in, listed it as V1, V2, V3, V4. That's not right. So I had to actually switch that to heading as yes to make it appear correctly. And right off the bat, you can see that we do have NAs in the data set, and that's gonna cause us some problems with doing overlays. Not the QQ plots. QQ plots handle it, but it's the overlay curves. And then just by default, I always check that box, strings as factors. So I said read it in as normality.data. I'm going to import it. And I'm going to copy that up into my R document. So I've got my practice, reading in data, reading in the data. So I've got normality.data. The other thing, since we just started this, I have to go up to the top and run my library car function, so that way the car package is accessible to us. All right, so I'm going to break this down to Q1. So for the homework, or for this practice, I ask you to make a histogram and overlay a normal curve. Number 2, make a quantile plot. And number 3, I asked you to perform a Shapiro-Wilk normality test. All right. And this is for each of our variables. And I asked you to interpret it, come up with an answer. Is it normal or not normal based on each of these assessments? So, first thing that it's going to do is give you practice doing all of these and repeated practice so that you'll become an expert at it by the time our exam happens. And if you're not an expert, you will by the end of this class, because we are assessing normality in basically every single data set that we're given. Second thing is that hopefully it'll show you that the quantile plot is going to be the easiest and most reliable way to determine normality, hopefully. You could say the Shapiro-Wilk is pretty easy because we have a clear definition that if a p is less than 0.05, it's non-normal. If it's greater than 0.05, it's normal. But since the Shapiro-Wilk is susceptible to sample sizes, we might come up with the wrong conclusion. So, Q1. So actually, we're going to look at the data set. So the data set, if you remember, actually I don't need this, let me drop this down, is a data frame with 8 variables, Q1, Q2, Q3, Q4. All right, so what we can do is come up with, make a new vector called Q1 for Q1 and make it one for Q2, or we can pass normality.data. So just as an example, so our options, I'm going to put this here. Our options for working with the data, with these data, are 1, utilize data $variable formatting in our functions. So that's number 1. Or number 2, create individual vectors for each variable. All right. If we use a data $variable, that works. It's gonna work. But when we do this, we have to be aware of missing data. We have to be aware of missing data. Now, for most things, we will use data $variable, because when we do statistical tests, we're dealing with the data frame that has the independent variable as a vector and a dependent variable as a vector. And if we use this type of formatting, then it ensures that each row lines up perfectly. Even with missing data, if one item in that row is missing, it drops the entire row. That's a good thing. All right? That's a good thing. But if we try to add overlays, if we try to do some functions that have that na.rm option, we have to remember to use it, because if we don't, then we'll get errors as we do vectors and stuff. Second option is to create the individual vector for each variable. And when we create that vector, what we can do is strip out all of the NAs ahead of time. So what we're going to do is we have 8 variables. All right. For the first 4, I'm going to use option 1. For the last 4, I'll use option 2, so that way you can see both types. So we'll use option number 1 for Q1 through Q4, and we'll use option number 2 for Q5 to Q8. All right, so we've got that in our notes. So first up, histogram with a normal curve. All right, so we're dealing with Q1. We're going to use option 1. So we're going to make our histogram first. So hist, right? We called it normality.data, and then $Q1. All right, I'm just going to make that. I'm actually going to do frequency equals false so I don't forget it. I'm going to make it and look at it. So number 1, I know we have decimals, so we're working with our proportions. Great, that's what we need. All right. Does this look like a suitable number of bars? I'd say yes. It looks pretty good. I don't think I'm going to change the breaks. So now the next thing to do is to add our overlay. All right. So hopefully you use the curve function, and it's dnorm of x, and then we have mean of normality.data $Q1. And what I'm going to do, since we're repeating this, I'm going to copy that normality data, so that way I can just paste it every time I have to. It's a lot of typing. So I've got dnorm x, and then we're going to do mean, and then SD, and then we've got add equals t. I'm going to do line weight equals 2, and I'm going to change my color to, I guess I'll use blue. And I'll try it. And I get it. Works out pretty good. So based on this, does it look normally distributed or non-normally distributed? All right, these data look non-normal. It looks skewed. Are we skewed left or skewed right? Skewed right, lean left. Yep, skewed right. All right, so that's our histogram. All right, now we'll try our QQ plot. So I've already loaded the car package, and it's QQ plot normality.data $Q1. Run that, and I get this. Normal or non-normal. Normal or non-normal? Pretty obvious. It's curved way outside of those confidence envelopes. 100% non-normal. So last one is Shapiro-Wilks. So Shapiro.test, and it is normality.data $Q1. I run this, I get here. Whoa, what did I do? Shortcut. The data are non-normal. Shapiro-Wilks test. Got W is 0.875. P-value is less than 0.0001. And again, don't worry about rounding yet. We will get to it. So in this situation, Q1, not normal. Very obvious. All measures, very clear. We're skewed. Skewness is represented as the curve in our QQ plots. So that's obvious. And then p-values, really, really small. That's Q1. Q2. So hist. I'm going to copy this too so I can just paste it every time I need to do that. I'm going to do frequency equals false again. I'm going to take a look at it. Oops. Yep.
I'm getting some errors over here.
What question? Number 1? Q1?
The one on all of them. Saying it's not a numeric thing.
Drop this down. Does it say Q1, Q2, Q3?
It says V1, V2.
Yep. When I do that, let's see if I can import it. Normality practice. Yeah, so when I do this, note the output. Right, it's V1, that's not correct. Because it marked the heading as no. You have to switch that to yes, and then you get Q1, Q2. So if you copied and pasted your code already, just do a here. Do heading equals T, or header equals T. Make sure you've got a comma after that, and then rerun that chunk. And then Q1, then when you do the drop down for your data, you should see Q1, Q2, Q3, Q4. All right. So I'm going to get my curve. Q2. Copy that. Copy Q2. Did it work?
Working on it. It looks like. The reason it said it needs to be numeric is that very first item is Q, so it read it as text. Yep. All right.
So here's Q2. I'm going to say the brakes looks okay. Not terrible. So I've got my curve. Add T, color equals blue. I'm going to do line weight equals 2. Make it a little bit. Then, notice it didn't work. Yeah, where is it? Curve is right. So I'm going to go down here and figure out what the heck is going on here. If I type mean of my Q2, I get NA. We have missing data. We have missing data. So if the curve function doesn't work, so there's nothing here. There's no blue line, right? All right, we're in proportions. That's good. So I'm going to do na.rm equals t, and I need that for the SD function as well. na.rm equals t. So what this will do is remove all of those missing data first before it calculates the mean and standard deviation. And once we do that, now we'll actually have a mean Now we'll have a standard deviation, and we can add our curve. That's different than if you forgot the frequency. Oops. So if you forgot to put frequency and you change the color and the line weight, I can see the blue line here. The curve function worked. It gave me a curve. Might not be the right curve, but it gave me a curve. The reason we saw that is because the frequency, we forgot to say frequency equals false. If we didn't do the na.rm equals t, then nothing appeared. No curve was put on. Instead of, oh, we have a missing mean, we have a missing standard deviation. Oh, we can't compute it. And R doesn't give us an error. That's the problem. So we're going to put here with the histogram. So would you say this is normal or non-normal? Yeah, I would say data are non-normal. So note, if we did not include na.rm equals t, then no curve is added. I guess then a curve is not added to the graph. Ridiculous. What happened? It like restarted on me. Then a curve is not added to the graph. And again, there's no blue. Since I change it, the line weight and the color, there's nothing. I do not see any of it. All right, so then what about QQ plot? QQ plot should work. Try it. Yep, it works. Is it normal or non-normal?
Non-normal.
Yep. I see curvature. Are you guys getting it?
No, you don't.
Yep. Which one? Are you
No.
right here?
No,
Oh, this one? QQ plot? QQ.
Okay.
So I see this curvature like this. That's what I see. But this is going to be kind of a tricky one because we see this like stair-step pattern. And I do have a note here to kind of address that. So why the stair-step pattern? Why the stair-step pattern? I mean, this other one that we made, the points lined up in a straight line. Why this stair-step pattern?
It's because they're integers, not numbers, so they're whole integers, not.
So it arises because of the discrete numbers or rounding. And rounding gives replicates of numbers. So what this stair-step pattern is really describing are the replicates. All of these points along the graph, they're the same value. All right, so R doesn't know how to array, well, which of the 10 5 values is first and which is last. It doesn't know. So it just puts them all at the same level, so it says, okay, that value is the same. These are all the same. So you'll get this if you're working with a discrete distribution. So if we had a binomial distribution or Poisson distribution and try to do a QQ plot, it'll look something like this. Or, is what most of the data that we'll have, is that we have, we take measurements and we round. Let's say round to the 10th place. We're going to have duplicates. We're going to have replicates. those replicates will fall out as being at the same level as each other. So the more replicates you have, the more obvious the stair pattern. All right, so then final one is Shapiro-Wilk. So we've got Shapiro Test. So data are non-normal. How do I know that? Because of the p-value. Wilk test. W. I'm just making sure I write it out, because once exam 3 starts, all of our answers will have a write-up. Not all of them, but most of them will have some sort of write-up attached to it. Data are not normal. So you can see we had a little bit of a hiccup when we tried to add the curve and realized, oh, there is no curve. Well, it's because we had missing data. All right. So Q3 is going to follow the same thing. Now, what I'm going to do is I'm getting tired of copying or typing. I'm going to do histogram. Everything that I just did, I'm going to paste it. And I'm going to update it to Q3. I'm going to take out this na.rm because I don't even know if I need it. I'm just going to update all of this so it is now in reference to Q3. And when I see that, I know no curve appeared, so I must need it. So na.rm equals t. na.rm equals t for the SD. When I run this, oops, the curve. Oh, I forgot a comma. There we go. So I just copied everything and pasted it, the chunks and all. Because it's repetition. Just make sure we have everything, we can address issues. So I get to this and I look at it. What do you think? It looks pretty good. I think here, yeah, probably. I'm going to say, instead of data are non-normal, I'm going to say data appeared normal. All right, I'm going to leave that note because this is another case where we had missing data. So I go to the PQ plot, update to 3. Again, we've got variation, got variability. Are all of the points inside of our envelope? The only one that I question is this down here, right here. But remember, it's the middle of the point. That's what matters. It's not the edges. So if I look at this, I actually think the middle of the point is completely inside that envelope. So this is one where I would definitely say data are normal. It's not just that they appear normal. At this place, I think we can say, yes, data are normally distributed. I'm going to delete this note because it's not a stair-step pattern. And then Q3 for the Shapiro-Wilk test. Data are normal. How do I know that? P-value is greater than 0.05. P-value is less than 0.46. You're gonna go back, copy, Q4. All right, so here's our Shapiro look. I'm gonna be pasting this again.
So why do you use the less than for the P?
It is, so why do I use it here?
Yeah.
Just for a little clarity. I don't know, you could say it's a, I know that the p-value that came up was 0.4593. I could say equals 0.46, that can work.
Okay.
But just, a lot of times, we're gonna use less than for, it's less than 0.0001, for like really small value. And if I start using that, then I like consistency, just use less than something. But we can always do equals, p-value equals, and wherever we round, that should give an implied limit then. So yeah, we can use equals, but we only go to 2 decimal places anytime we're above 0.01. So yeah, we'll have rounding rules as well. All right, Q4. I'm gonna go ahead and do Q4. I'm gonna leave that NA, that RM equals T. Gonna leave that in there. I don't have to mess with it. We're slightly off the graph. We can adjust our y-axis to fix that. Or, since we're just using this for assessment, so if I was gonna include this in a paper or on a poster or in a presentation, I would definitely adjust this so that we can have the entire curve.
Did you get enough difference?
What's that?
Our histograms do not match yours.
Yeah, they don't. They do not. Yours looks different. No, mine goes 0.08. I guess what we'll do. Anyone else get theirs that looks like this?
They have different numbers.
Yeah, are we centered? Yeah, so our average would be something like 27 and a half. Let's see, let's overwrite this file. Maybe I opened the wrong file. Let's see here. Overwrite file. Save, link as. Go to here. So far everything else was looking the same, right? Wait, hold on. Hold on. Yeah, I'm clicking on the wrong spot. Save link as. There it is. Normality Practice Csv. Replace it. Yes, I do. I do want to replace that. Let's make sure it actually got replaced now. Okay, Normality Practice. New save. Let's try this. Normality data. That's good. Oh yeah, that's looking good. I'm gonna guess W stayed the same. 2 looked to be the same. 3. We're on 3? No, we're on 4. 3 looks good. 3 looks good. There it is. That looks better. Better. Alright. What does this look like? Looks like 2 peaks. I'm going to increase the brakes just to check it. 15, nothing. Should do 25. Ah, 25. Look at that. 25 looks a little bit better. I think that's a little bit clearer. I think the 2 peaks makes a little bit more sense. This looks like a bimodal distribution. This bimodal distribution, at least in our fields, makes it, or at least tells us that there might be 2 groups in our data. This would be one group, this would be the second group. So if we thought they were all one group, we might need to look more closely. Go back, hey, did I, are these 2 different species? This is a great example. Are these 2 different species? Right? That's it. So what does our curve look like? Yeah, I don't even need a normal curve on this. Just the fact that we have 2 peaks is enough to say that the data are non-normal. So yeah, it notes the presence of 2 peaks is sufficient evidence to claim non-normality. We didn't even need that. And again, the 2 peaks, I don't want you to add a bunch of breaks and say, well, I got a peak here and a peak here. No, you got that because you added huge number of breaks. And like each bar has like 1 or 2 items. This, clearly, each bar has quite a few numbers in it. This is clearly a bimodal distribution. And when we do our QQ plot, yep, this is that like this is like a dual S-shaped curve. And again, this is evidence that we have 2 different groups. Mm-hmm.
I have another question.
Mm-hmm.
It's like QQ plots aren't working.
Did you load the car package?
I thought so. Oh wait,
I got mine right at the start. It says library. Yes. Yes. Now, yeah, the QQ, car loaded. So go ahead and try that. Here it is.
I had to read it again.
You get it?
Oh yes.
What's that?
I'm gonna read it.
All right.
All right, so this is it. I'm pointing this out because in the future, when we work with like a t-test or a ANOVA, the assumption is data are normally distributed within each group. So if we ignore the group classification, we'll get curves that look like this. The assumption isn't the entire variable is normally distributed. The assumption is that each of our groups has a normal distribution tied to it. So just, again, pointing things out that we'll see. So yeah, this is clearly non-normal. And Shapiro Test should pop up as non-normal. All right. Q5 through Q8. All right, so these last 2. So this is how we did like $, data $. All right. So for these next ones, we're going to use that option 2. Next, for variables, we will use option number 2, which is, which means we are creating vectors for each variable. And this will work since we're just checking normality for a single vector. If we are doing normality for groups and stuff, you're going to see that we work with the data frame. All right? So when creating the vectors, we want to remove missing data. The function to do this is na.omit. All right. The function is na.omit. So I can go to the help file and look up na.omit. There it is, search results. so you can see what it looks like. Na.omit works on data tables, all right, and vectors. So what it's going to do is go row by row. If there is an NA in that row, it drops the row. All right. The problem with using it in a data table is that it could drop the entire row. And a lot of times we don't want to do that. So if our data table has 5 or 6 columns, and I'll use morphology. Morphology is a great example. You took, who's measuring anything? Measuring skulls. I guess that we'll keep that. So we've got, let's say we're measuring left canine, right canine, cranial diameter, width, back of the head to the nose, and so forth. So we'll have, let's say, 6, 7 different variables that we measure. Well, there's a possibility that maybe one of the canines is missing. All right? If you're using the morphological data as a set to distinguish between species, why would we drop an entire skull from our analysis just because it's missing one of the teeth? We've got all the other measurements. So if we use na.omit on that entire data frame, we drop that entire row and then we stop using it. That's not good. It's better than if when it comes time to using those teeth, those left and right canine, to remove them individually, like on an individual basis for our analysis. So what this will do when we pass a vector is to go row by row and remove each item of the vector, and then we will save that new vector after we remove all of the objects. So this function goes row by row and removes rows with an A in it. All right. So we are dealing with, we're starting at Q5. So what I'm going to do is create a new vector called Q5. And in that vector, I want to save my normality.data $Q5 variable, but I want to remove all of the NAs. So I'm going to do na.omit and then normality.data $Q5. All right. And I'm going to run that. Now, just as a demonstration, to show that it works, here's my Q5 vector. All right, the Q5 vector, oops, there it is. Q5. Yep. So the Q5 vector, this is it. These are the values. These are the values. And then it tells you that we have omitted 1,500 entries. And the entries that it tells you that it omitted is row number 2,501, 2,502, and so forth. So there's 2,500 in here. So if I do just, I'm going to do structure of Q5 to give me the structure. It tells me it's a numeric vector with 1 to 2,500 data points. If I do structure of my normality.data $Q5, you're going to say it reports 5,000. So what we've done is basically stripped out all the NAs, saved it as a Q5, and now we don't have to worry about using na.rm. So with this, I have Q5 going on. I'm going to do that for Q6, Q7, and Q8. And every time, so I copied and pasted it 4 times, I'm just going to change it and say, okay, well, this one's Q6, this one's Q7, and this one's Q8. And I'm going to run them. So now I have Q5, Q6, Q7, and Q8, and it appears in my environment and tells me that, okay, Q5, I've got 2,500 values. Q6, I only have 20. Q7, I have 10. Q8, I have 60. So now we can go ahead and start doing all of our analysis. So Q5 Oops, here's a histogram. So histogram with normal curve overlay, right? So I don't need normality.data $Q5 anymore. I made the vector, I can pass it right to Q5. Make sure I use frequency equals F. All right, and then I'm gonna use my curve function. So mean of Q5, SD equals Q5, and make sure add equals T. And then I'm gonna do line weight is 2 and color equals blue. And it should work. Voila. Didn't have to worry about NA.rm at all. Made the vector, checked it. Uh-oh, what's your red? Oh, D norm,
Messed up commas.
parentheses,
Yeah.
and then X. So D norm,
Yeah.
parentheses, X, comma. Hit delete. And delete that in front of me to that
Yeah.
Now I think that should.
I knew it was something like that.
Yep.
I was sitting here messing with it.
All right, that was Q5 for the histogram. Go ahead, we can do the rest for the Q6, Q7, Q8. We're dealing with smaller sample sizes now. So what we're gonna do is, I want you to have this done for Monday, since we had some issues getting this together. We'll start reviewing it, and then on Monday we'll move ahead. Looking ahead, let me look at the presentation for this. Hypothesis testing and confidence intervals. So part of this hypothesis testing is kind of theory. Where does the p-values come from? You know, how are we doing that? And then calculating standard errors that we can utilize or generate 95% confidence intervals. And we'll see how far we get on probably Monday. Yeah, Monday or Wednesday. And then we'll know if at least part of that lecture will be on the exam. All right. So yeah, finish up the QQ plots, Shapiro walk, and then we'll just kind of cruise through this on Monday. Spend a little bit more time just interpreting and not necessarily writing out everything. All right.